Okay. Good morning, dear student. Last class we have discussed, how to compute angle and magnitude of given GFS, HFS, the transfer function. We have considered a point P and we try to calculate the angle with respect to the point P and the magnitude of the GFS, HFS with respect to the point P. Okay, so now we are going to apply angle and magnitude condition, okay, analytically as well as graphically, okay, on the following unity feedback system. Okay, we will consider this unity feedback system, and we were trying to do analytical as well as the graphical, what we call computation of angle and magnitude. So here the point P, we are considering it as S is equal to minus 0.25. S is equal to minus 0.25 is the point P, we are considering it for angle and magnitude condition. Okay. So let us take this G of S into H of S, the open loop transfer function. The angle condition becomes angle of G of S into H of S is equal to angle of K divided by S into S plus 1 into S plus 2. Correct? Angle of this transfer function we have to calculate. What is the angle? Angle contributed by numerator, it is always positive, minus angle contributed by denominator first root or the first pole, angle contributed by the second pole. You can see here the sign minus. Always angle contributed by poles are negative. Angle contributed by the numerator roots are positive. And the angle contributed by the third pole, here we have. This has to be equal to multiples of 180, we call it as plus or minus 180 into 2k plus 1. That is what the angle condition which we have mentioned in the last class. Okay, so this all the angle, that is angle contributed by the numerator and angle contributed by the denominator, this algebraic sum, numerator we have plus and all the denominator, the poles angle contribution we have negative. This algebraic sum should be equal to plus or minus 180 degree into 2k plus 1. This is for the angle condition, correct? So now we have to compute the angle of K at S is equal to minus 0.25, because with respect to a point we compute angle. Okay, simply we cannot give angle. Always with respect to a point we will be computing what is that point. That is S is equal to minus 0.25, and again this S at minus 2.25. Again this root I have to compute at minus 0.25. Again, this angle contribution at S is equal to minus 0.25. I have to do it. Okay. Now we know that this is not a variable in S. This doesn't give me any angle. Whereas here I have, S is equal to minus 0.25. That is an angle at S minus 0.25. Angle due to, S at minus 0.75 and at, 1.75. Okay. So since the point what we have P is on the negative real axis, the line joined to that point, line joined to that point, we can have only two angles. Either it will be 0 or it will be 180. Only two angle possible, correct? This 0.25, if you take a anti-clockwise direction formed, okay, by pole at 0.25 to a point at 0.25, then you will see that, that angle is 180. The other two you can see this is 0.75 and this is 1.75. So these two are this is anyway this is going to the right of the S plane. This you have minus 0.75. So angle contributed by these two we have 0, whereas angle contributed by this is minus 180. Okay. So we say that total angle contributed by this for S is equal to minus 0.25, we have minus 180. Okay, what we are looking for here, the angle condition, it has to be equal to plus or minus 180 into 2k plus 1. So multiples of 180, you should get it as an answer. So we have found that this is matching. Minus 180 is a valid angle. So we say that, the S is equal to minus 0.25 is a point on the root locus because angle condition is matching. Okay. So now we have magnitude condition. Okay. So magnitude of this we can calculate. So how to calculate? We know that the magnitude of this should be equal to 1. According to the magnitude condition, this should be equal to 1. Okay. So what is the S value? S value is minus 0.25. With respect to this point, we are trying to calculate the magnitude, right? Okay. So now we see that what is the corresponding value of K. Okay. So to satisfy that magnitude condition, what should be the value of K? We are trying to calculate here. Okay. According to the magnitude condition, we are going to define the value of K. So how to do it? Take this ratio, substitute S is equal to minus 0.25. Okay, you will get, like this. You are substituting S as 0.25. Okay, simplify, then you get a value for K as K is equal to 0.328. So what I did, you can see that in the previous slide, what I did is, we can use magnitude condition to determine the value of gain at any point on the root locus. Value of K we are trying to plot, because we wanted to find the magnitude for a point S is equal to minus 0.25. So corresponding K we are trying to calculate. How to calculate the corresponding K? Take this transfer function, substitute for S is equal to minus 0.25, and we know that the magnitude condition says that magnitude of this will be equal to 1. Just substitute S and keep simplifying, you get a value of K as K is equal to 0.328. Okay. So this is how, we will calculate the values of K through the magnitude condition. And this is how we will be computing the magnitude. Okay. Magnitude and the angle. Okay. So now you can check whether the following points are on the root locus or not. Graphically as well as analytically, you can do it. Okay. So, and if it lies on the what root locus, you have to calculate the corresponding gain value K. Okay. So you have two points here. I have randomly taken 2 points here. You can see that these 2 points are complex in nature. Okay. So this complex point we have. So, graphically how to calculate magnitude and how to calculate angle we have seen in the last class. Just apply that method and just calculate angle condition and magnitude conditions should satisfy. Then we say that the 2 points what we have, point 1 and 2, anyway calculation you will be doing separately. These 2 points we can say that lies on the root locus, otherwise no. Okay. If it lies on the root locus, you can apply magnitude condition to calculate the value of K. Okay. So if it lies on the thing, you can calculate, otherwise you need not. Okay. So this is a homework, you can do it. Take these 2 points, repeat the procedure of calculating angle and magnitude. Okay. Graphically as well as analytically. You have to learn and you have to be comfortable with the gain and magnitude parameter, which we'll be discussing often. Okay. Next is, construction of root locus. From this point onwards, you have to listen very carefully, because we will be learning how to construct the root locus. Okay. How to construct the root locus. We have different steps here. We have around 8 to 10 steps depending on the transfer function type. It varies from 7 to 10. So we have to look into all these steps while drawing the root locus. Okay. Step number 1. What is the first step? The first step in constructing a root locus plot is to locate the pole zeros. Pole zeros, what we have, pole zeros of, open loop transfer function in S plane. Okay. You have to consider the open loop transfer function, identify pole zero plot, identify the open loop zeros, open loop poles in the S plane. That is the first primary job you have to do it. So I have an example system here. What is the open loop transfer function? Since it is a unity feedback here, Whatever block I have here, I take it as an open loop transfer function. So open loop transfer function, I'll take this block as it is because the feedback is unity. So I have GFS into HFS as an open loop transfer function, which is given by K divided by S into S plus 1 into S plus 2. First, you have to draw the pole zero plot. Imagine an S-plane here. At S is equal to 0, there is a pole. You can imagine here, separately you have to equate these three things to 0. Get the value of S. Go to that particular value of S here on the real axis. And you have to identify the pole position. So at S is equal to 0, I have a pole. At S is equal to minus, I have a pole. At S is equal to minus 2, I have a pole. So I have identified the poles here. Since there is no zeros in the transfer function, I could not locate the zero since it doesn't exist for this particular problem or this particular case. So this is the step 1. You have to do it while constructing a root locus. Okay. What is the first point? Identification of open loop poles and zeros in the S-plane. Okay. That we have done it. Next, we have to see, is there any root locus exist? Is there any part of the root locus exist on the real axis? We have to check. Okay, entire S-plane, anywhere, roots can lie. As the K value we change, anywhere in this S-plane it may lie, but all the part we don't take it here in step 2. We just take the real axis. Okay, existence of root locus on the real axis we just study here in the step 2. Okay, then we will just see further how to complete the root locus. That we will see in the coming steps. Step 2 is just to identify, is there any root locus exist on the real axis or not. Okay, this real axis is very, very wide, ranging from 0 to minus infinity to the left side, and 0 to plus infinity. That is what the axis axis wideness I'm talking about. Such a wide axis we have here. To the left I have minus infinity, to the right we have minus infinity. So now suitably I have to now fragment this real axis. How do I fragment? How do I make pieces? How many pieces I should make it so as to analyze whether in that segment root locus exists or not? First I have to do the segmentation of the root locus. How do I do it? I know that these poles are the salient point on the real axis, correct? On the real axis, the salient points are the pole positions. Okay, anything which changing here in the real axis is the pole position. So what I do is, keeping these pole position into picture, I'm going to divide the entire real axis into 4 regions. I'll make 4 regions. What is the region 1? Region 1 is to the right of this pole, to the right, entire right side of the real axis, right of this pole, I'll take it as first segment. Okay, to analyze whether the root locus exists or not. Okay, second segment, what I do is the line or the real axis between these two poles. Okay, that is pole at the origin and the pole at -1. In between, whatever the section I have, real axis, I take that as section 2. I take third section here between these two roots, that is root at -2 and the root at -1. Whatever the length I have, that is, I'll take it as the third section. And the fourth section is from -2 to infinity. That is what I have, fourth section. Okay. Now what I should do, as I fragmented this, I will just see whether root locus exists in these 4 sections separately. Whether it exists or not separately, I'll just check for each section. Take the first section, that is to the right of this pole. How to check whether the root locus exists here or not? Randomly identify a point P on this side. That is section 1. What is section 1? To the right of the pole at 0, whatever you have, that is from 0 to plus infinity, that entire length, you can imagine a point P anywhere in this section. Okay, imagine a point anywhere in this section. Say for example, P1 I identified here. Anywhere you can choose that. Okay, now I'll calculate whether this P1 satisfies the angle condition or not. Magnitude you keep it aside. First I'll verify whether the angle condition satisfy or not. If the angle condition satisfy, what I conclude, this point belongs to root locus, or this point lies on the root locus. Okay, if it lies on the root locus, what is the inference? Inference says that the section 1, entire section 1, there exists a root locus. Entire section 1, that is from 0 to plus infinity, the entire length of the real axis, will be having root locus. That is, root locus exists there, we call it as. Okay, so now we will see the angle condition. Okay, what is the angle condition? How to compute angle condition graphically? We have learned, join all the poles to this point, salient point P1. That is the procedure, correct? We have to join all the points to the point P1. If I join this thing, all the three lines lies on the real axis. Okay, now what I have to find out, the anti-clockwise angle I have to find out. Since all the anti-clockwise angle with respect to the point P found to be 0. Okay, say for example, this pole you are joining to this point, then there is no angle made, correct? It lies on the real axis, so there is no angle made. That is, which angle I am talking about? The anti-clockwise angle. If I say, it doesn't exist, that is 0. Again, for this pole, if I join, again it is 0, 0. That's what this line here we have mentioned. That is all the three poles will be contributing angle 0. So this does not satisfy the angle condition. What I want the angle condition, either I should get plus 180 multiples, or I should get minus 180 multiples. Okay, so here it's not matching. The angle condition, it's not satisfied. So we say that the section 1 what I made does not contain root locus. Okay, that you will not find root exist in this section. Okay, next what I do is, I will go to the next section. This is the next section between s is equal to 0 to s is equal to minus 1. I have second section. I will identify a point P randomly, anywhere you identify. I will just see whether root locus exists in this section or not. Again, what I should do, all the three poles you have to join to this point. Try to calculate the anti-clockwise angle made by those three lines. Okay, see, from this pole, the anti-clockwise angle, if I take it, it is making 180 degree. Whereas this pole, if I join to this point, the anti-clockwise angle is 0. Again, this point, if I join this point P2, then anti-clockwise angle found to be 0. Only this pole is giving me the angle 180. Okay, so the angle condition is matching, correct? So pole at the origin is giving me angle 180, whereas these two poles is giving me angle 0. So what is the conclusion we can make here? The multiple of 180 I am getting, correct? See, angle condition is matching. Since angle condition is matching, so we say that there exists the root locus. There exists the root locus, that is between these two poles, there exists a root locus. That is in the second section, I will find that root locus exists. Now I'll go to the third section. Same procedure I'll repeat. I'll join all the three poles to the point. If I join all the three poles, this pole and this pole is giving me what? An angle 180. Whereas this pole giving me an angle 0 with respect to this point. That is anti-clockwise angle. So what I'll be getting, the two poles, that is at origin, whatever pole I have, at s is equal to minus 1, whatever pole I have, these two are giving me 180, whereas this is giving me 0. Algebraic summation gives me minus 360. Okay. See, angle condition is not satisfied. angle condition is not satisfied. So you know what, we have to get, we have to get plus or minus 180 into 2k plus 1, where k can take the value 1 2 3 so on. Okay, if it takes 1, so I'll be getting 180 into 180 into 3, correct? So next, if I give a value for k, if I give a value of k, say 2, then it is 5. Okay, that is, I'll be getting 3 5 7 so on. So you will get some odd multiples of 180 we will be getting. So if it is not matching, then we say that angle condition is not satisfied, so root locus does not exist. Okay, so it is plus or minus 180 into 2k plus 1 is not satisfied, so we say that root locus in that section does not exist. Whereas in the last section, if you take it, if you calculate the root locus, then we say that angle condition satisfied here. It will satisfy here because all the three gives the value 180. This also 180. This also 180. This also 180. So you will see that angle condition is satisfied. Root locus exists. So this is what the red line says here. In this section, root locus exists. In this section, root locus exists. So we conclude that on the real axis, only in these two regions there exists a root locus. Here it doesn't exist, and here it doesn't exist. How could we conclude that? We calculated by taking a point in random here, and we found that it doesn't lie on the root locus, so root locus doesn't exist there. Now, we always say that this is step number 3 while constructing a root locus. Step number 3, we always require an asymptotes. What are asymptotes? Asymptotes are the lines which guide the root locus. Okay, in which direction it has to move, in which shape it has to move, what we call, in which orientation it has to move. It all is decided by the asymptotes, or the root locus guiding lines, we call it as. It guide the root locus. We keep the asymptotes as a reference and we draw the root locus because the direction is followed by the root asymptotes. Okay, so asymptotes are very important. Asymptotes is the straight line approximation of a curve. Okay, root locus is a curve whose straight line approximation, we call it as an asymptote. Okay, so actual root locus will be the curve, whereas asymptotic approach, if I say, it will be like this line. Okay, so we call this as, this asymptotes will guide this root locus, we call it as. Okay, so we have centroid for asymptotes. Okay, because we found that the number of root locus for a given open loop transfer function depends on the number of poles or number of zero, whichever is greater. If you're having 3 poles, then you will be having three root locus. Okay, so if because from every pole, from every pole there originate a root locus. From there, or root locus is originated, we call it as. So how many asymptotes we require? Number of asymptotes will match with the, what we call, number of root locus which exist in the transfer function. Okay, so number of root locus, how do we calculate? Number of poles or number of zeros, whichever is greater. Okay, that many root locus exist for the given transfer function. Okay, given open loop transfer function. So now if there are 3 root locus exist, say for example, then you require 3 asymptotes. 3 asymptotes exist. So these 3 asymptotes intersect each other at a point. We call it as a centroid. Or else I can say that the asymptotes originate from the centroid. I can say that. Okay, so all the asymptotes intersect at what we call it as centroid. So this is a common point where all the asymptotes meet. We call it as centroid. With these asymptotes also having an angle. Okay, what is this angle? Angle of asymptotes, we call it as. This is the angle made by the asymptote with respect to the real axis. with respect to the real axis, whatever the angle made by these asymptotes, we call it as angle of asymptotes. Okay. So what is the third steps? Third step is a step wherein which we takes the help of asymptotes. So asymptotes are essential to construct the root locus because we keep these asymptotes as a guidelines to draw the root locus. So number of asymptotes requirement depends on the number of root locus which exist. So if you are having 3, then you will be having 3 asymptotes. So asymptotes will be having always an angle and a centroid. Okay. So more than one asymptote if exist, we will find that these asymptotes are intersect at a common point called centroid, and angle made by these asymptotes with the real axis, we call it as angle of asymptotes. Very important. What is the equation for the angle of asymptotes? Angle of asymptote, we call it as phi. Phi I call it as, which is having the formula that is plus or minus 180 into 2k plus 1 divided by n minus m. What is the small n? Is the number of poles. What is m? That is number of zeros. For the function which we have taken, g of s, h of s is equal to k divided by s into s plus 1 into s plus 2. What is the equation for angle of asymptotes? Which is plus or minus 180 into 2k plus 1 divided by n minus m. We have to take it. According to the transfer function, number of 0 is 0. Okay. So number of n stands for number of poles, m stands for number of zeros. So poles we have 3 and zeros we have 0. We don't have zeros, so number of zeros are nil, so number of poles are 3, so 3 minus 0 we have to do it, okay, in the denominator. Now k values I have to change as 1, 2, 3, so as to get the different angles. Okay, so as to get the different angle, we have to change the values of k. Okay, so how to do it? So change the k value here. So you will get one angle plus or minus 60 by just changing the value k. You got the first angle as plus or minus 60, plus or minus 80, plus or minus 300, plus or minus 420. Okay, these are all the angles you got it. Okay, so since the angle repeats itself as k is varied, if you vary k, it will repeat. The distinct angle for the asymptote are determined as 60 minus 60, minus 180 and plus 180. So you will see that as you keep on changing the k value, you will not find any other angle. You always find plus or minus 60 or plus or minus 180. That only will repeat. So these are all the 4 angles we have. Okay, so thus there are 3 asymptotes having angles plus 60, minus 60 and 180. Okay, so these 3 are the asymptotes we will be considering it so as to draw the root locus. So now asymptotes angle we calculated, we have to calculate the centroid. So before we can draw these asymptotes in a complex plane, we must find the point where they intersect the real axis. Okay, intersection of these asymptotes with real axis, there is a common point. All the asymptotes interact with the real axis at one common point. We call it as centroid. Okay, that we have to calculate. The centroid of asymptotes we call it as. Okay, that is intersection of asymptotes on the real axis. We have to calculate. Okay, so how do we calculate centroid? We have a formula here. Centroid of asymptotes is equal to summation of poles minus summation of zeros divided by n minus m. What is n? Number of poles. What is m? Number of zeros. Okay, so summation of poles and poles minus summation of zeros, we have to do it. So we know that at 0 there is a pole, the 1 there is a pole, and 2 there is a pole. That summation we have to do it. So at 0 there is a pole, at minus 1 there is a pole, at minus 2 there is a pole that I have taken. I don't have zeros, so I have 0 here. So in the denominator I have to take number of poles minus number of zeros. So number of poles are 3, number of zeros are nil, so I have taken 0 here. What is the centroid value? I got it as centroid value minus 1. Okay. Now I can compute, I can draw the asymptotes now. Okay, what I do, first I'll identify the centroid. So first asymptote is drawn with an angle 60. There is a one asymptote exists. The other one is minus 60. The third one is with plus 180. Okay, so three asymptotes exist. So these three are the asymptotes, and this is how we will be drawing the asymptotes. Okay, now next is we have done this, what we call it as the asymptotes part is over. Now let us take an example. Consider the following unity feedback system. The transfer function of open loop is this, we call it as, because this is what we have negative feedback. It's a unity feedback we have. So the given block here, whatever we have, we consider it as open loop transfer function GFS into HFS. What I have to do it, I have to calculate existence of root locus on real axis, angle of asymptotes I have to calculate, and centroid of asymptotes I have to calculate. Okay, very simple. So you can do this at home, very simple procedures. What we have to do is, this is the transfer function. Root locus existence on the real axis, how do I do it? You have to first draw the pole zero plot. Pole zero plot, you have to do it, and you have to divide the real axis into different sections. In each section, you have to identify randomly a point, and you have to match the angle condition. If angle condition matches, then you can say that there exists a root locus. Otherwise, root locus does not exist. Okay, so that is what we call it as existence of root locus on the real axis, and you have to do it and you have to plot that. And angle of asymptotes, we have a formula for that. Just substitute and simplify. We have totally 4 poles and 1 0. So n is equal to 4 and m is equal to 1 we have. Substitute and you will get the values of the angle of asymptotes, and centroid also we have a formula. You have to substitute and you will get the centroid. Okay, very simple. This is what we have, the step 3, and that is what we call asymptotes, angle and asymptote centroid calculation, that we have learned now. So next step I'll take up in the next class. Okay, that is next step, breakaway point, breaking point calculation. I'll be taking up in the next class. Okay, thank you.